How's it going? Today we're going to wrap up chapter 6. We're going to do 6, 7, and 6, 8. They both tie together a lot because they're dealing with coordinate geometry. So we're going to be looking at these polygons on like the X and Y axis and plotting points and that kind of stuff today. And before we get started, we want to make sure that you remember some key formulas that we're going to be using this chapter. The distance formula. Okay, be sure that you know that. To determine if anything is, I don't know why this doesn't come through very nice, that's a congruent sign. To determine if things are congruent, we can use the distance formula. If we want to find if something is bisected and it goes through the middle, we'd find the midpoint. And then if you want to see if things are parallel, we're going to use our slope formula, because if they have the same slope, then they would be parallel. So those are the different formulas we're going to be using and why we would use each one. All right, so we're going to start with this. It says triangle DEF. Okay, we're dealing with a triangle, not a quadrilateral here. Triangle DEF has vertices at 0, 0, 1, 4, and 5, 2. And they want to know if it is scalene, isosceles, or equilateral. Okay, as a quick review, remember that in equilateral triangle, all three sides will be congruent. In an isosceles triangle, 2 of the sides would be congruent, and scalene means none of the sides are congruent. Now, we are not going to go plotting a bunch of stuff. I said plot these points. We're not really going to use a graph. We're going to try to do this without a graph. And we just have to know that we've got this triangle here, whatever it might be, and D, E, F, and D is at 0, 0. E is at 1, 4. And F is at 5, 2, and we're just going to use those coordinates. And in this case, since we want to know what's going on with the side lengths, then we would be doing the distance formula. All right, so we're going to do the distance formula 3 different times. We need to find the length of all 3 sides. So let's start off with, and I'm going to try to do this real organized for us. Let's find the length of DE. The length of DE is going to be the square root of, and then I'm going to do, if you look back at your formula if you need to, it's x minus x squared. So I'm going to do 1 minus 0 squared plus, then I'll do it with the y's, 4 minus 0 squared. And now let's simplify that up. That's the square root of 1 squared plus 4 squared. And that equals the square root of 17. So that's how long DE is, the square root of 17. Now I'm going to do this again for each side length. Let's do it with EF. Big square root, x minus x. So I'll do 1, I'm doing EF, so 1 minus 5 squared. Plus, now do the y's, 4 minus 2 squared. And then go ahead and do that operation. 1 minus 5 would be a negative 4. But if you square negative 4, you get positive 16. Plus, 4 minus 2, that's 2. Squared is 4. So I'm left with EF equaling the square root of 20. Now I can reduce these, but ultimately I just want to know if they match, and they don't. So right now I could check off equilateral. It's not going to end up equilateral. Let's try the last one. I'm going to do DF. Big square root, x minus x. So I'm going to go with 5 minus 0 squared. Plus y minus y, I'm going to do 2 minus 0 squared. So that's going to end up 5 squared, that's 25, plus 2 minus 0 squared, that's 4. I'm left with DF equaling the square root of 29. That's another different side length. All 3 of them were different. All right, so which type of triangle do I have? Scalene. And this is kind of my justification, my proof of it. Don't just sit there and guess which one it would be. You should have proof of it, right, like we did here. All right, let's try another problem. Now this time it's a quadrilateral. We have 4 vertices, and we want to know if it's a rectangle. Okay, so a rectangle. Different things that we could do for that. I'm going to go ahead and draw the picture for us. Draw it like a rectangle just in case it happens to be, but it's in M, N, P, Q. All right, so I have different things that I could do. There's lots of options here. A rectangle has 4 right angles. So what I could be doing is I could do the slopes, and then they would be opposite reciprocals of one another. Okay, so that would work. I could do, let's see, what else does a rectangle have? I'd have opposite sides congruent, but that wouldn't be enough, because just because I showed that this leg here is the same as this leg, and then this one's the same as this one, well, it could still just be a parallelogram, because that's from parallelogram. So that would not be enough. I don't think I would want to try that. How about diagonals congruent? That was something, if I could show the diagonals congruent. But remember that in a trapezoid, it also, an isosceles trapezoid, it has congruent diagonals. So I really think probably my best bet is to show the slope on all of these and show that I get opposite reciprocal slopes for those. All right. I don't think I need to do it 4 different times. I think if I could show this one is perpendicular to this one. Let's start with that, I guess. Let's start with finding out if is M, because really we're going to do the slope, Let's see what we get. So I'm going to write this, trying to keep this organized for you again, because you end up doing this a bunch of times, you lose track of what you did. So this is for MN, slope. And I'm not going to rewrite all my ordered pairs. I'm just going to peek up here, so I'm using M and N. So the slope formula, y minus y, so I'm going to start with the n. I'm going to go 4 minus 1 over, then I'm going to do x minus x, negative 1 minus 0. All right, that's a 3 over negative 1. I get a slope of negative 3. Now let's try, so that's this slope. Now let's try this slope. So I'm going to do MQ. MQ would be, all right, so maybe I should have changed colors. I'm going to do MQ, so I'm going to do M and Q here. Do y minus y, 2 minus 1, over x minus x, 3 minus 0. 2 minus 1 is 1, 3 minus 0 is 3. Ooh, that's a 1/3. I like it. It's opposite reciprocals. So I know right now that MN and MQ are perpendicular, so that creates a right angle right there. All right. Now what I'm going to do is I'm going to go ahead and do the same thing over here. I'm going to find out if this and this are perpendicular, because I've already done MQ, right? I already have that one. So now let's do PQ. Y minus y. Okay, P and Q. Y minus y. 2 minus 5. Remember, it doesn't really matter which one you start with as long as you're consistent on your y's and your x's. So I did Q minus P. So I got to do Q minus P again. And here I end up with a negative 3 over a positive 1. That's a negative 3 slope. I like it. That's what I needed. Opposite reciprocal. And let's just to be on the safe side, let's confirm it one more time. Let's do the last side, NP. What do you suppose it should be? Hopefully 1/3, right? Let's check it. NP. This one and this one. Y minus y. That's a 5 minus 4 over 2 minus negative 1. It's a 1. 2 minus negative 1 is a 3, 1/3. It matches. Awesome. All right, so I've got opposite reciprocal again. I'm going to go ahead and say yes. It has 4 right angles. Now this is the same quadrilateral, and now what I want to know is it also a square? Well, I've shown that it's a rectangle. And if it's a rectangle, then it's going to have to be some type of a parallelogram. A rectangle is just a specific parallelogram. So I know that the opposite sides are parallel. I know that the opposite sides are going to be congruent, but because I know that this is going to be congruent to this, and this is going to be congruent to this, because I showed that it's a rectangle. I know that's going to have to happen. I already have the right angles. I know that, so that part of the square is good. But for it to actually be a square, I need not only for these to be the same, I need these to be the same. So I'm going to check 2 of these sides, and all I have to do is check one set of these. I'm going to find the length of this one and the length of this one. I know that these are going to match. So my hope is that this and this actually end up being the same length. All right, so let me throw those letters back in there. This is M, N, P, Q. So to find out their length, remember that's a distance formula thing. So I'm going to find the length of MQ. Let's start there. Big distance formula, doing M and Q. All right, so the distance formula is x minus x. Again, doesn't matter which one you start with. I'm going to go 3 minus 0 squared plus, starting with Q again, y minus y, 2 minus 1 squared. And I change it up on which one I start with because I usually like to dodge negatives. So I usually like to take the bigger number minus the smaller number. The problem is that it isn't always the same with the x's and the y's, so just do whatever you want. 3 minus 0 squared, that's going to be 9. Plus 2 minus 1, that's 1, 1 squared, that's 1. All right, so MQ is going to be the square root of 10. Now let's check it and see if PQ is also 10. If PQ, or root 10. If PQ is also the square root of 10, then I'll have myself a square here. All right, so P and Q. X minus X. 3 minus 2 squared. Plus, do the same thing with the y's. 2 minus 5 squared. All right. 3 minus 2, that's 1 squared, is 1. Plus 2 minus 5, that's negative 3. But if you square it, it goes back to positive 9. Ooh, looky there. That's going to be square root of 10. Yes. If I've got opposite or consecutive sides like that congruent, that's going to force all 4 sides to be congruent. So I'm going to say, is it a square? Yes. All sides congruent. Oh, and perpendicular. All right, we're going to move on. We're going to look at 6.8, applying coordinate geometry. Now, the thing with coordinate geometry, you're dealing with ordered pairs a lot. And this in 6.7, that's what we did. We used those formulas, and you had actual ordered pairs. In this chapter or section, we're really looking at just relationships and understanding what would have to be the case if you were looking at something on a graph. And you won't have specific numbers every time. This is a classic kind of just, do you understand what's going on? An ACT kind of question that they love. Do you understand big picture? Okay. What are the coordinates of the vertices of each figure? So we have a rectangle, so you have to know all your properties of rectangles. The height is A. Okay, so the height, this height right here is A. You could write it on either side, doesn't matter. That's the height. And the length of it is 2B. Well, it says the y-axis bisects EC and RT. Okay, so if this is bisecting, then I know that this is the same length as this. And if you look at what it, since the whole length is 2b, how far over do you think, how long do you think this little segment is? Well, yeah, that'd be b. And then this would be b, which would get you 2b for that total length. Okay, got that. Now the question, though, are what are the coordinates of the vertices? Now notice there's no numbers here. They're not asking for numbers. They want to know in relationship to A's and B's, what would that coordinate be? So let's think about this point right here. And you're just looking at how far over, how far up, and that's your coordinates. So right there, I would say the coordinates for T, well, if this is the origin right here, over 0, that's 0, 0, so I'd be over B, that's how far over, but I didn't go up at all, so that coordinate would be B0. That's what they're looking for. Okay. If you did R, what would change, do you suppose? Well, you're going left. That distance is still B, but you're going left. So you're going to be negative B, 0. Okay, let's look up here at point C. What would that ordered pair be? Well, to get to that ordered pair, you have to go over this far, over B, and up A. So that would be the coordinates of C over B, up A. All right, you try E. What do you think E is going to have to be? All right, you should have gone left B, so that's still negative B, and you're going up, so that's positive A. Okay, let's try another one. This time we have a kite, it says, and we're still looking for the vertices, the coordinates of the vertices. Let's see what we know. IE is 2A. The whole thing here is 2A. All right, it does say here that the x-axis bisects IE, so then I know that this and this will have to be equal. And then if it was 2A, then I know that this length is A and this length is A. There's your 2A. KO, this little segment here, is B, and OT is C, because those are obviously not the same length there, so those are different measurements. All right, let's see if we can find some ordered pairs. Let's start with T over here. Okay, to get to that point, remember that your origin is right here. So how far over did you just go to get to this point T? Well, you went over C units. And how far up? Well, that'd be 0. So my coordinates there at T would be C0. All right, let's try K. How about that one? How far over did you go from the origin? Well, you went left, so it's going to be negative B. And how far up? 0. All right, let's try I. What do we got here? To get to this one, I went, well, from the origin, I didn't go over at all. My origin's right here, so I'm going to go over 0 and up A. To get down here, I'd be over 0 and down A. So those coordinates would be 0A, but this one down here is 0, negative A, because you went down. Okay, that's not too hard, do you think? We can do this. Oh, they're going to make it a little trickier for us. Here we go. The diagram shows a general parallelogram. Okay, got the parallelogram, all those properties, with a vertex at the origin, got it, and one side along the x-axis. Okay, that shows it all nicely there. What are the coordinates of point D, which is the intersection of the diagonals? All right, so we have to kind of go back to parallelogram, and what do you know about the diagonals in a parallelogram? Well, they're not equal to each other. That is not going to be the case. This diagonal you can see is longer than what this one is. But what they do is they bisect each other. So I know that D is going to be the midpoint of this segment. I know D is the midpoint of this segment. Now, it's not necessary really to do the midpoint twice. You can really just pick which one do you want to work with. Do you want to find the midpoint here, or do you want to find the midpoint here? Either way, it's going to get you that coordinate. I like the 0, 0. Shall we try that then? 0, 0 to here. I'm going to work with those two. I'm going to work with this coordinate here and then the coordinate 0, 0, and I'm going to find the midpoint of it. Anytime the things bisect each other, you're doing midpoint formula. All right, so we haven't done one of these yet. Midpoint formula. Okay, so this is for OB midpoint. This is where you have this big ordered pair, and you're just finding the average of the x's, and then you're finding the average of the y's. So to find the average, I'm going to take my x's, add them, and divide by 2. So I'd have 2a, this is that b, and that's a messy coordinate. The x coordinate is 2a plus 2b divided by 2. All right, let's add the y's and divide by 2. That'd be 2c divided by 2. All right, and then we want to kind of simplify that up. You're taking this entire quantity here and dividing it by 2. And the only way you can really divide by 2 is you take both of those terms, the 2a and the 2b. They both have to divide by the 2 because it's a big fraction right there. Well, that's easy enough to do. They both have a 2 on them. So 2a divided by 2 is just going to be an a. 2b divided by 2 is just going to be a b. That will simplify to just a plus b. Comma, and 2c divided by 2 is just going to be c. So right there are our coordinates of D. No numbers, just working with variables. All right, here's our last one. Shows a trapezoid. Doesn't say that it's isosceles, just says, oh wait, okay. Shows a trapezoid with a base centered at the origin. Is it isosceles? That's the question. Okay, is it isosceles? Well, we'd have different ways to show that. You could, isosceles means that this leg and this leg are the same. Well, I could do distance formula, see if I get the same thing. That would work. The other thing that I could do is the diagonals in a trapezoid are congruent. So I could do distance formula here, distance formula here. What do you think? What looks easier? Does one necessarily look easier than the other? I'm not sure. I'm looking at letters and seeing how would I do that. If I did this distance formula, I'd have an A, a B, and a C all involved. Over here, I'd have an A, a B, and a C all involved. If I did diagonals, I'd have an A, a B, and a C. Okay. All right. I don't know that there's one that's better than the other. Let's go ahead and just do the definition. Let's show that this leg and this leg are congruent. Okay, you know what? I'm going to change my mind there. Well, yeah, no, I'm going to stick with that. I don't know. They put the diagonals in there. I felt like, are you wanting me to use the diagonals? I don't know. I'm not sure it matters. Let's just choose one. I'm going to stick with I'm going to try to show the legs are congruent. So I'm going to work with R and T. Let's find the length of RT. This is a distance formula problem, big distance formula. All right, so I'm looking at R and T. Here we go. Everything's in letters. Nothing's going to be pretty. Not even the same letters, so nothing's going to cancel nice. I'm just going to work with it. So I'm going to go with x minus x. I'm going to go negative b minus a. Ooh, minus negative a. Okay. Squared. Plus. Now let's do the y's. Starting with my r. That'd be a c minus the y on the t. Okay, this one's nicer. That's better. I can live with that. Okay. Over here, though, this is kind of messy. RT equals, and this is a negative b minus a negative a, going to turn into positive. So I have negative b plus a squared plus, this would simplify to c squared. Now I might have to do more with that. So I'm going to leave the space underneath it open because I may have to go back to my algebra. Remember when you'd square this binomial, so I'd have to write it twice and do FOIL on it? I might have to do that. I don't know. I'm going to wait and I'm going to go do A and P, and I'm going to see what happens on A and P. Maybe it'll just match perfectly and I won't have to do anything. So I'm going to find the length then of AP. All right. These look a little bit nicer, not so many negatives, I guess. All right, and then I'm going to go x minus x. So I'm going to do b minus a squared plus y minus y, c minus 0 squared. All right. So again, I'm just going to leave this as a b minus a squared plus c squared, and then I'm going to compare. And when I look at these, they look a lot alike. You got the plus c squared, I like that. But is this necessarily the same as this? Notice the signs are messed up. The b is positive, whereas over here it's negative. The a is positive, whereas here it's negative. So I'm not sure that those are really the same thing. And like I said, what I could do is I could check it and FOIL that out and see if I end up with the exact same thing if I ended up foiling. Because if you square it, maybe those negatives go away and it doesn't really matter. Let's try it. Let's see what happens. So I know I'm going to have the plus c squared thing going, but let's go ahead and see what happens with the first binomial. I'm going to write negative b plus a times another negative b plus a. Is this coming back to you from Algebra 1? I know, it's been a while. Now I'm going to do FOIL. Negative b times negative b. It's a positive b squared. Now I'm going to take my outer, negative b times a, and my inner, negative an a times a negative, that's another negative AB or BA. Really, that doesn't matter the order. Really, look, those kind of match. Those are like terms. A lot of times that happens with outer and inner. All right, and then last, plus a squared. And then, of course, I still have my plus c squared sitting out there. But let's kind of clean this up. I have a b squared minus BA, and another minus BA would be a minus 2BA plus a squared, and then still got the plus c squared. All right, now, let's see if I do FOIL over here on this other one, if that's going to come out the same way. I'm going to write b minus a twice, because I'm squaring it. Oops, undo that. And then I'm going to FOIL, so do first, that's b squared. Outer is a minus BA, and inner minus A times B again. Oh, looky there. I'm gonna switch it, keep it in the same order, but minus BA, and then your last, a negative A times a negative A. That's a positive A squared. You still got your plus C squared out there. Those match, don't they? Look, you got a negative BA and a negative BA. That's what we had here. Going to turn into a negative 2BA. The B squared is positive. The A squared is positive. Still have the C squared tucked at the end. All right. We had to work on that one a little bit. That's okay. It's okay to work sometimes. These ended up being the same thing. Now, what in the heck were we doing? Do you remember? All right, let's go back. What we just showed is that this leg right here is the same length, I do my distance from it, is the same length as this one right here. All right, and that's really what mathematicians do. This is what they do. They work with very generic values before they can say, oh, this is always going to happen. They work with generic values and prove things, we call it analytically, actually. When you deal with just the variables like this, it's analytic geometry, and you're kind of showing it would always work, regardless of what this A, B, and C, what these values are. You just showed that it would always work. So it's kind of a way of doing a proof. All right, that's all I have for you. Good luck.